and I'll put it up if anybody wants to watch it again tonight before the exam. You're mad, but maybe that's okay. Okay, can you see the screen?
Yep.
Cool. So this is the deck of highlights from the course that I put together. There's about maybe 5 slides from each of the modules. So I'll take it through. There's a couple of, maybe have less. We'll go through and we'll see what we've got. So ask questions as we go along, either drop them into the chat or put your hand up and jump in, interrupt me, because today is all about your guys' understanding of what these kind of fundamental concepts. So we'll skip over 1A. We talked about that last week. That was about some of the fundamentals of the language terminology, and we'll get into the data section. So really the principal concepts here in the 1B in the language data is, fundamental to everything that we do in this language technology is that permission and consent is the most important thing. You can't build language technologies without having permission and consent, proper informed consent of the people whose language recordings, language material, language knowledge that the systems are being built with. And we can't build language technologies without language data. So, it's really a fundamental principle that you've got to get permission from the people that you're working with to build the technologies. Curious thing about Australia is that the legal frameworks in Australia don't recognise the community control or the community ownership around language. The legal framework is well and truly behind where the community's kind of mindset of language rights are, and so you might have legal rights to use material. You also need to check community permissions and community kind of the community's rights in material. In terms of legal frameworks, we've got copyrights and we've got licenses to data, and in the course we talked about different sort of licensing frameworks, including the Creative Commons licensing, which is commonly used for licensing creative materials like artistic works, imagery, sound recordings. Creative Commons is less used for code. If we're licensing code, we're more likely to use licenses like the Apache or MIT frameworks. Of course, we looked at. Whoop, I think my speaker just changed. Can you still hear me okay?
Yeah, we can hear you.
Sorry about that. So in the course, we looked at some language recording collections, some corpora that were licensed under different frameworks. There was Creative Commons licensing that also had other licenses attached or other kind of licensing restrictions to it. So while we might have a legal framework, we also need to check that there are other conditions around the usage of the material that we're working with. A significant thing here in this last point, that language barriers make gaining informed consent difficult. So if I am a monolingual English speaker and I'm trying to obtain informed consent to use or work with language recordings in a different language with other people whose English might be their 6th language, then there's a major language barrier there around what are we going to do with this language material. And this might come up if we're working with language
recordings to develop an AI system. How do you explain what is AI to someone who may not have come across these kind of technologies, that the words AI might not translate particularly well into other languages? These are all things to consider in terms of getting consent. A list of some of the types of licenses that have been used. This relationship source is a really interesting one, Kei Kitanga license, a relationship source whereby people might open up access to either code or to data based on an understanding that the people who are going to use it will use it for goodwill and for the benefit and the strength of both the owners and the users of the material. Creative Commons, Apache, MIT, some of the common um, open source licenses. Another major topic in the language data module was about the encoding of the data, and we talked about the encoding of audio in terms of WAV, high fidelity encoding of the audio data. Unicode is a system that without which our language technologies would be a real mess. Without Unicode or some similar universal standard, then one language technology might not be able to communicate, may not share data well with another language technology. So if Nick developed a program that worked with some text, and I developed another program that worked with some other text, if we don't share the same encoding system, then it's likely that the messaging in between these systems would be garbled. So the Unicode is a universal standard for ensuring that when a system means to use the letter A, then other systems understand that that's the character that is intended. It uses this code table kind of lookup system based on some things called code points, a series of numbers that can be represented in different ways. So the code points can be represented in this U plus 0041 system. So that tells me that in the code chart, column 4, row 1 gives me the letter A. So Unicode number 41, U plus is the prefix. Unicode 41 is the letter A, and this extends to a Unicode table that is thousands and thousands of rows deep. They can all be represented by these U plus symbols. They translate to the binary representation of it. And again, you can see in the orange, in this graph here, the orange 100, 001 is again a row and column, column and row designation for the same point. So Unicode and binary and hexadecimal are different ways of representing the same character. These standards are really important, without which the whole kind of interoperability of language technologies would just crumble. So ASCII was a system that was around before Unicode was invented, and was a very small system used for a minimal set of English characters and didn't transpose particularly well to any other language on the planet. So Unicode was developed in the 90s to support more languages. And these days it also carries things like emojis and other sorts of symbols like arrows and such. So the difference between Unicode and the fonts, this is a nice representation that Zara gave us, that the Unicode point, the 41, represents the character A. Now, what that looks like in the different presentation systems will depend on the font. So fonts tend to be drawings of characters that are connected to particular code points, and the drawing will change, like the graphical representation of that letter will change. But regardless of which font we're using, because of this intermediate system of the Unicode, then the letter A, we can change the font. We know that we're always getting a letter A. If we change a font in the old days before Unicode, you could change a font and the glyph, the letter A, might end up being represented by a letter P or some other kind of wacky character. And so it was very, very, very confusing. So another significant point about the language data is that language technologies need clean data. And to do that involves data preparation. So we saw this very recently with the annotation of the sign language material, where you can imagine if you had annotated the sign shapes and got some of them wrong, how that might affect the language technologies further down in the chain. We need to be really particular about how clean our data is. That comes from the point from recording, so separation of speakers or separation of signers. If we're doing videoing of sign material, can we use individual microphones on speakers to really get very clean audio signal per speaker? We want to minimize things like air conditioning, clocks, wind noise, anything that's going to disrupt the audio signal from a really clean speech. Making the most of uncompressed audio formats like WAV for the audio recordings. It gets more complicated with video recordings where it depends so much on your budget. So a high quality, low compression video camera can cost up into the hundreds of thousands of dollars. It's more likely that video recordings are quite heavily compressed. So in this case, if we're doing language documentation with video, it's really important to use a separate audio recorder as well, because they'll tend to have much higher quality audio recording than you can get with a video camera in a reasonable kind of price bracket. Once the material's been recorded, then the transcription or the annotation brings its own challenges, and we experienced this a few times during the course where we were transcribing recorded material either by transcribing the sign or from the working with the digits in the earlier modules. We have a few points here about how to clean language data when we're preparing it for speech recognition or translation. So making sure we have typographic errors checked. Normalizing orthography is a big thing. So whether it's working across different spelling systems like American English or British English, these conformance makes, if we can conform the different spelling systems into a single one, then we can provide a better data set for the system to learn from. If we had two different spellings of the word color through our data set, then if we're using a probabilistic language technology, then we're halving the effectiveness of that system. It's important to take out non-lexical text such as laughter and unclear speech, and we tend not to transcribe back-channel things like affirmatives, yep, those types of affirmations of confirmation. While they're important in other senses in terms of validation of the conversation, they can cloud the annotation for speech recognition or translation. we pull out punctuation. A lot of the language tools will do this automatically, but it's certainly worth doing it prior to training, and something to be aware of if designing or building language technologies is that some languages use punctuation for lexical significance, in that as markers for, is this word a noun? Some languages use marks like exclamation marks, hyphens, dashes, commas, and various punctuation marks as part of the language system, the way that the language is writing. So we also have to be careful not to strip those things out if they are significant for the language in terms of the meaning. There's a few technologies that can do things like removing background noise. There's some of them listed there. So speech recognition module, the key things here are that we have acoustic models, pronunciation models, and language models. We put audio in, we get text out. The language model, this was covered early on and in much more detail later in Module 5. The essence of the language model is, well, the important things to think about here are the n-grams, that if we're training a language model, we can either train it on a word sequences, each word individually, or we can look forward and backwards to see the words and their neighbors, the bigrams and the trigrams. It's unlikely that n-gram of more than 5 is used. As we saw later on, the storage requirements there, they're training n-gram systems with 5 or up to 8, it can just get crazily expensive computationally. So the n-gram systems tend to be in the shorter order, between 1 and 5. So the language model is the part of the system which understands which word follows preceding words. Pronunciation model, also called the grapheme to phoneme model, or the G2P, is the way that the words are pronounced. And there are a few different ways that happens. It can be done through neural networks. It can be done through very simple script-based replacement systems. Fundamentally, the words are broken down into the way that they're pronounced. And the acoustic model is like the alignment of the audio features to the phonemes or the phones. And so we can see in this diagram, in this graphic here, that the bottom row, these are the words. The second bottom row is the pronunciation of those words. And then we have the acoustic features. This is the MFCC. And then we have the top 2 rows of the waveforms. So the acoustic model aligns the audio features to that phone. What is that sound? And how is that sound represented in this system? So the representation of these of the phones is often through the IPA, International Phonetic Alphabet system, but there are a few other standards that can be used as well. So this is a common process in speech recognition, speech to text, and also in the reverse in text to speech. Now, in the speech recognition systems, we use decoding graphs to kind of bring these different models together, where our acoustic signal relates to the phoneme model, the phonetic model, and pronunciation model, and the language model. So if we have a series of sounds, then the machine can bring those back to the series of phonemes that are most likely for those sounds, and then what are the series of words that are most likely for that sequence of phonemes. Now, the Kaldi system that we use in ELPIS uses finite state transducers to build that graph. The systems in ESPNet and the kind of end-to-end neural networks don't use FSTs, but these Kaldi FSTs, they've been around for kind of 10, 15 years or so, or longer. Kaldi's been around about 10 years, and they're quite reliable and certainly useful for situations where we have not enough training data to build a neural network. The decoding graph is made of the H, C, L, and G, the audio features, the phones. So the H and C are that's the audio model, and the pronunciation model and the language model. So these get combined into this big decoding graph. And the representation of the FSTs here is this visual representation. We've got the circles are the states in the FST, the lines in between them are the arcs, and this drawing has weights on them in that we have the label on the arc and the number after the label is the weight. So the weight is the likelihood of that path being chosen in between the two states. So we can make our way through the decoding graph by following the path with the best weights. So see if you can work out the best way through that graph on your own. Bold circles are the initial states, and they often have an arrow coming into them, but not in this representation. And the final state, or it has this double circle around it. Final state means that everything up until that point has been accepted, and that's an appropriate endpoint for it. Here's another lattice. This again shows, so the lattice is a subset of a big decoding graph. The lattice shows the pathways through the decoding graph. Now this representation has numbers in front of labels, but the numbers here are not weights. So the different representation here, we've got the input label, so there's intuition, and then the colon, and then another intuition. So we have an input label, a colon, an output label, and then a slash and the weight. So you'll see in this next one, this is not a weighted representation, so we don't see the weights in this lattice. This is just telling us what the input and the output is. So the input here is an integer, and that would map to a phoneme or a phone, and that 15 would map to a phone, and that would map to a speech and acoustic feature as well. Best overall. So if we are following this through the whole chart, we want to go all the way through. So I'd say using data is better, I think would be the optimal pathway through that. So yeah, I guess it's a bit of both. You pick, now it also depends on the method that's being used. So I think we saw that in the language models module later on, there are methods that will just look ahead to the next state, and they'll pick the highest probability to the next state. And there are different methods that pick the highest probability, the sum of weights across the whole path. And so you get different results if you're picking the highest probability across the whole kind of tree. Then you might end up with different results than if you're picking the highest probability between each state. Okay, so the finite state automaton are systems which accept input values, and transducers convert inputs to outputs. That's the big thing. So in this representation here, the input is being the input number 15, which represents some kind of acoustic feature, is being converted into this output value, which is a word. So this is a finite state transducer, which is in converting input acoustic features into word sequences. All right, so NMT is not an area that I have much strength in, but the key things here, again, the data is a set of parallel corpora, so we're talking about thousands of sentence pairs before we get good results. Production systems generally use millions of sentence pairs, so there are techniques around at the moment to work with. So Ashley, who presented this module, is working on technologies to get reasonable results with fewer sentences.
Ben, sorry to interrupt, but there's a question in the chat, I think, about the weighted searches.
Yeah, I think I just talked about that. Was that okay, Helena? Yep, cool. All right, so for the translation, an early step is the tokenization, and this works kind of better with some languages than others. We talked about this a bit last week. For English, we can tokenize words quite well, although there are situations where punctuation can confuse things. So in those situations, you would need to have some kind of punctuation model to deal with that. And then for languages like written Chinese Mandarin, then this may not tokenize particularly well. I actually talked about the way that translation is evaluated, and the fluency, the adequacy, and the overlap. Again, this was covered last week in the review. We want to be sure that when we're evaluating the translation, that we consider how good the translation is, and recognizing that the way that we evaluate is there are different metrics to it. So while a translation might be very lexically accurate, it may not interpret particularly well. So the fluency, the adequacy, and the overlap are different ways to ensure that the understanding of the translation or the usability of the translation is adequate. So to consider that these 4 translations, please send this package to Pittsburgh, or send my box Pittsburgh. Please send this package to Tokyo. I'd like to deliver this parcel, destination Pittsburgh. They are maybe all close in terms of the words that they've used, with the exception of Tokyo being a significantly problematic error. Then these metrics of fluency, adequacy, and overlap seek to measure how well is this translation going to work. So the couple of different methods for doing the translations, the recurrent neural networks. There's a simple neural networks, and we had gated recurrent units, and the transformers. I wonder if anybody else wants to jump in to talk about the difference between these. I think Janet covered it a bit last week. Do we want to talk about them more now, or shall we keep cruising on? I think the essence was that the simple networks worked fine when you had a limited data set, and then as you had more data, then the other networks tended to work much better. Transformers are certainly the neural networks in vogue.
Yeah, so I don't think people need to know the details of transformers, because you're going to be taking a neural network course if you really need to learn them in detail. But I think it's important to realize that different kinds of models will work better depending on how much data you have. And so the simpler models, although they don't seem as powerful, they will work better if you have smaller amounts of data. As soon as you start having the gated recurrent units, you will need a lot more data, because the gating itself has different computational requirements.
Okay, thanks, Janet. So text-to-speech, what are the main TTS approaches? We heard about concatenative, parametric, articulatory, and these more recent ML methods, tachytron and wavenet. So concatenative is very basic, slice some audio up, glue it together, and you get something that sounds like, it might sound like someone speaking, but it's very disjointed and very crude. Parametric tends to smooth some of those joints. The articulatory systems model the vocal tract, and it sounds like it's a good idea. It tends not to work at all in practice because they're extremely computationally intensive. And then we experienced some of the tachytron and wavenet methods in the tutorial. So one of the early techniques is diphone synthesis. You record every phonetic translation in the language, you slice them up. So it's not recording the a, but, k sounds, but it's recording the halfway in between ab and halfway into the b. So you get in between the middle of a transition between two phones to the end of the transition between two phones. It's all about this kind of joining up the transitions in the phonemes. So, and you can do this with either diphone or triphone, or even whole word unit synthesis. And this tends to be a way that people approach it as an entry into building TDS systems. Unit selection takes it to that point of recording whole words or whole phrases and using those in the playback. And then we have tachytron and wavenet. So tachytron uses a sequence-to-sequence neural network model, converting characters to the waveform. Oh, sorry, not the waveform, to the MFCCs. And as we experience in the tutorial, it gives pretty good results, but it does need a lot of data to build up. The wavenet, similar sort of system, it uses the waveforms, and it builds up an audio sample by sample. Oh, sorry, the little animation doesn't work. But the thing about the wavenet is that it grows as it generates the audio samples. So from the tutorial, I think we experienced that the tachotron was was maybe the most realistic sounding system. Still a question of how do you evaluate. So as we saw with the translations, how do you evaluate translation systems? We need to consider how do we evaluate the effectiveness or the usefulness of the TTS systems. The metrics here are intelligibility and naturalness. So how well can somebody understand the words that the system says, and how human-like is the speech of the system? And there was, I think it was the WaveNet that we used in the tutorial, had a really high-pitched hissing sound through what it was playing back. It was kind of surprising, but again, maybe that could be trained out with a different, or maybe that could be built out with a different training system. The anatomy of the TDS is different from or back to front to the speech to text. So we have our verbalization system, then where we convert numerals into the lexical forms, and we put it through the pronunciation model where we break the words down into it's like the pronunciation dictionary, and then our acoustic model tells us how to pronounce that. So the left part of the diagram here is courtesy of Dan, and the right part of the diagram here is courtesy of David. So we have the simple version and the more elaborate version of each of the stages in the production in the TDS system. Chatbots. So the very early chatbots, Eliza, developed to parody the psychoanalytic kind of technique in the 60s. And then there were a sequence of ones which then built upon that, but we could see that there was a very scripted responses to questions. Along came Alice and AIML, the artificial intelligence, artificial intelligence markup language, where we can code up questions and responses in this pattern and template markup language. Categories, patterns, and templates. So the pattern, we can see here, the patterns are capitalized. This is a kind of non-formal standard, and the responses in the template are in either plain text or some computational data, so which is what C data stands for, where we can include other markup language. So this looks like some sort of XML or not XML, or some sort of HTML-ish response. Along comes speech bots. These are underpinning the consumer technology of Siri, Google Home, Alexa, and we have this agency pair question answering kind of dynamic. So we ask questions to our devices and we expect to get answers back. We don't really go in for long-winded conversations or storytelling. You ask a question, tell me a joke, we want a joke back. Tell me a good joke, we want a good joke back. Tell me a dad joke, we want some awful joke back. So these adjacency pairs is a term that's worth remembering. The series of questions and answers. And then the way that these action question dialogues are implemented, we tend to have these things called slots, where we can say book me book an appointment or make it a meeting at 3 o'clock. Then those requests and the subject of the request and the time go into different slots into the action that the bots perform. Something that comes out of these chatbots, which is very different from the speech recognition tech, is that we're getting into this kind of conversational pragmatics where it's not so much about what the person says as the way that people say it is as significant. It's, um, conversation is messy. People speak over the top of each other. Turn taking is not neat, is what this refers to. So if I speak and then typically in a conversation, if I speak and somebody else will speak over the top of me or vice versa. And in a sense, for a natural conversational chatbot, we would expect the chatbot to do that as well. So we wouldn't expect the technology to wait until I'm speaking before it would interject or to give some kind of back channel. For naturalness, then that back channel is kind of expected. And these conversational chatbots have to understand that not everything that we say is literal, and especially if you're building a chatbot for an Australian, you've got to deal with situations where like sarcasm does not translate particularly well into speech recognition. Doesn't deal well with sarcasm. So can a chatbot understand when you're being sarcastic if it's just turning your speech signal into text to operate on? When people say yeah, nah, these kind of conversational norms can be really problematic for a chatbot to interpret. So meaning is socially grounded. The chatbots have kind of got to be social and cultural agents, where the chatbot's got to understand the social context in which it's operating. And thus we get to social robots, which is maybe a whole other course. And so Dan talked with us about communication accommodation theory, which is this situation where two or more conversation participants are sharing content. How are the characteristics in their speech aligning or misaligning? How do conversational agents accommodate each other in terms of repeating what each is saying or understanding what each is saying? So this communication accommodation theory tries to wrap all of these kind of conversational dynamics in a system that we can kind of deal with through the chatbots. There's some. I don't think I included the graphs. So we have the language technologies like discourse, which can look at the patterns in a communication exchange over a period of time and look at where repetition happens. So there are language technologies that can help to visualize this. Language models, again, so this goes deeper into the LM stuff that we had in the early part of the course, where we looked more at the probabilities of word occurrence. So again, language model, probability of a sequence of words. The more commonly occurring have a higher probability. N-grams, so the key thing here in the n-grams, if the n-gram is small, then the long distance dependencies don't get recorded, or they're not captured. So here we have, if in our sentence, gorillas always like to groom their friends. If our n-gram is 2 or 3 or 4 or 5, then we don't see the relationship between gorillas and their. However, if the n-gram is too big, so if our n-gram was like 8 gram, which would see that relationship between gorillas and their, it just gets crazy big to store and then to process and to run our hypothesis through. So there are a few techniques to deal with these, to accommodate using small n-grams and try to find those long distance relationships, but they are out of scope of this course, and so they won't be covered in the exam. Ngram language models have a disadvantage in that they don't count for word similarities. So the movie was fantastic, or the movie was awesome. The probability of awesome in that the movie would not be found, because the relationship between fantastic and awesome, to us, we understand the language, they are similar words, but they wouldn't be picked up in the language model. So the wordgram similarity in language models, they don't consider word similarity. To do so, we need to use neural language models, and we use methods like word embeddings to recognize similarities in words. And we played with the GPT-2 system in one of the tutorials to experience what it was like to generate some language. And we saw that with these technologies, that I think the key takeaway is that these language generation technologies are extremely good. And we saw that a system had been used to write an article about that a lot of people had trouble discerning that it was not written by a human. So the key takeaway from that is that those systems are really good, and with those systems come great risks as well as the benefits. Now I should kick over to Jess to take over from here, but maybe if I can summarize this module, Jess, and see if I haven't missed anything significant. The key things here is that we've got sign and gesture, and they're quite different systems, and we can consider building language technologies for both. The sign, if we think of sign language, it's a formal language compared to gesture, which is an informal language. Well, informal, non-language, informal communications. So sign language being a formal communication system, gesture being an informal communication system. We have sign, we have lexical kind of signs, and gesture we have non-lexical. So the components of sign, we have hand shape. So what is the shape of the hand? Let's see if I can do it. What was it that? Orientation, which way is the hand pointing? Location, location in terms of close, proximity to the body, near the head, near the chest, all these sorts of things. Movement, is the hand moving or is the shape moving? And expression. So these are the ways that the signs are coded. Just talked with us about the concept called the disability dongle. So this is where technologies are created for people based on an uninformed perception of what is a problem. So we get this a lot in user design situations where a designer thinks they've got a great idea to make someone else's life better, and they might take on the persona of that person for a day and invent something to make that person's life better. In most situations, it turns out not making that person's life better and can often be really problematic. So disability dongle is this great kind of a term for situations where people who, they might have the best of intentions, but are coming in and building technologies for situations where that technology, the tech is really not needed or necessarily wanted. So we saw that in a couple of examples with the stair climbing wheelchair, where actually, a $30,000 wheelchair is not necessarily the best design response, when maybe a ramp would have benefited more people than that individual person who probably couldn't afford the wheelchair anyway. So how do you make good technology instead? Work with people, listen to users, and really work on projects that people actually want, not on projects that you think people want. technical considerations for sign data sets are quite different from speech data sets. So we've got this whole kind of this visual element here in terms of it's not just the shape of the hand. So we've seen a lot of technologies being built for sign and gesture where people measuring the data, you put a data glove on and measuring those points in space and missing out on all of this kind of proximity information. There's a lot of facial expressions and mouthing part of signing, and so limiting the data set to the data points of a hand misses out on a lot of this extra information. There's a few different ways of recording that data, video, skeletal stuff, using Xbox, or what are they called? Those Connect body posture capturing systems might be a way of doing it. And just as in speech language, then sign language has intersigner variation, and we have dialect and accent differences in, so there's no kind of single standard. There's a lot of individual variance. There's as much individual variance in sign language as there is in a spoken language, where in a spoken language somebody might lisp or stutter, and you might have those same sort of effects in a sign language as well, sign communication as well. So considerations around where data is recorded from, similar to speech systems, it's broad community support is needed to ensure that you've got coverage of the range of the ways that people sign, and again, how to get buy-in from deaf signers. It's important to work on projects that matter and involving people at all stages of the project. Yeah, there's a couple of points there about techniques to collect data. I might skip over them. And given the time is coming short, I think that's about the end of it. So having skimmed through, I didn't quite meet my half-hour mark. But are there any questions about all of that?